Following on the heels of the previous video on trigonometric integrals, powers of sine and cosine, we're now going to look at powers of tangent and secant, which again work nicely together because their derivatives are connected to each other. The derivative of tangent of x is secant squared of x, and the derivative of secant of x is secant of x times tangent of x. So they are related to each other in terms of their derivatives. Much like what we saw with the powers of sine and powers of cosine, one of the techniques that's going to come off here very often is to split off factors from the original integrand that will later on be used as our du in integration by substitution. In this case, we'd be looking for splitting off two factors of secant x and therefore being able to convert the remaining integrand to powers of tangent. The idea here being that this would allow us to use u equals tangent x with du is equal to secant squared of x dx. Another option here, depending on the nature of the integrand, would be to split off one factor of secant along with one factor of tangent. In this case, since that is the derivative of secant of x, that means we would want to convert the integrand to secants. This would allow us to do a substitution where u is equal to secant x, so that du would be equal to secant x times tangent x dx. Now, in dealing with this, let's not forget that by splitting off factors, whether it's two factors of secant of x or whether it's one of secant and one of tangent of x, we will then be reducing the powers that appear in the original integrand. And once again, in order to convert them, we're going to need some identities. Unfortunately, there aren't identities as clean as sine squared of x is equal to 1 minus cosine of 2x all over 2, and the corresponding cosine squared identity. But we do still have a Pythagorean identity that involves tangent squared and secant squared rather than sine squared and cosine squared. We can use the tangent and secant form of the Pythagorean identity, tangent squared x plus 1 equals secant squared x, to help us in converting powers of tangent to powers of secant and vice versa. Now we need to be careful because in order to use this identity, we again need to reduce down to even powers of tangent or even powers of secant, positive even powers, in order to make use of this identity. So we have to be careful when we're splitting off two factors of secant, or when we're splitting off one power of secant and one power of tangent, that we have to be careful that while we're doing that, we are leaving in the integrand an even power of whichever one we're trying to convert. So if we're going to split off secant squared of x, and we want to convert the remaining powers of secant into tangents, then that means that we had to have had a positive even power of secant to begin with. We would have had a positive even power of secant to begin with so that we can split off 2 and still have an even power and thus use the Pythagorean identity. For the other situation, if we want to be able to split off a factor of secant x and a factor of tangent x, and then convert all remaining tangents to secants, we're only splitting off a single factor of tangent of x, in addition to a single factor of secant x, but we're going to keep our focus on the tangent of x here. We're only going to be splitting off a single factor of tangent of x, which means in order to leave behind an even power that we can use the Pythagorean identity for, we have to start it out with an odd power of tangent. Sounds like a lot. And if you want to try and remember it in terms of, well, in the situation of an even positive power of secant of x, I do this. In the condition of a positive odd power of tangent, I do this other thing. I prefer to think of it in terms of what you are able to split out and leaving behind an even power no matter what you're splitting off. That was the same basic goal in dealing with the powers of sine and cosine as well, that if we're going to split off any factors, we wanted to make sure we left behind a positive even power to allow us to use the Pythagorean identities. So let's look at an example here. We'll start with something a bit interesting, but not unlike what showed up as an example in the sines and cosines video. Here we're going to have an integrand that is tangent cubed of x over the square root of secant of x dx. In a case like this, we have a non-integer and also a negative power of secant. Either one of those conditions is going to make us want to kind of shy away from that factor. We ideally want to look for positive integer powers of one of the trig functions, and that's the one we're going to kind of want to work with whenever we can. So we're going to keep our focus on the tangent of x here. That's the one that's easiest to split off. However, in both scenarios here, we have to split off at least one factor of secant of x. We either had to split off 2 factors of secant of x in order to use u equals tangent x, or we had to split off a factor of secant of x with a factor of tangent of x. So one way or another, we're going to have to deal with that secant of x in the denominator underneath that square root. To help us in doing that, the best way to start is probably to not have the secant be in a radical and be in the denominator. As with most things in calculus, it's actually easier to work with if you have a negative fraction exponent than if you have a radical in a denominator. So our goal here is going to be to split off a factor of tangent, thus reducing the power to an even power. So I'm going to start with that because that's the easier one. I'm going to leave a little space here for the secant. I'm going to split off one factor of tangent, thus reducing the power of tangent left to an even power. This will allow us to use a Pythagorean identity to replace tangent squared of x with a secant squared of x minus 1. We'll get to that in a moment. If we're going to be converting the remaining part of the integrand into secants, then I need to have split off the derivative of secant to be our du. So I've already split off a factor of tangent. I'm now also going to have to split off a factor of secant of x, which When you have a fraction power, specifically a negative power, that becomes a little less obvious. But ultimately, what splitting off a factor does is it simply means we're going to reduce the original exponent by 1. If you look at the tangents, that's exactly what happened. To take one tangent out and put it off to the side meant the power went from 3 to 2. I subtract 1 from the power as I remove one factor. In that way, we can grasp the concept of removing a factor when the power is already less than 0. If we subtract 1 from the power on this secant of x and drop it to negative 3/2, we can therefore have a secant to the first that is brought out to the side. And while that seems a little weird, that again is really all factoring out a factor is doing, is reducing the power of the original by 1, or by however many factors we pull out, in this case 1. So we've got our secant x, tangent x, dx off to the right. That is going to be our du when we get to substitution. But before we get there, we need to convert this whole thing into secants. So I'm going to leave this first guy alone because he's already a secant. But the tangent squared, using the Pythagorean identity, can be replaced by 1 minus secant squared. And now, the secant of x to the negative 3/2 can simply be distributed. We would now have secant of x to the negative 3/2 times 1, which is just secant of x to the negative 3/2, minus secant of x to the negative 3/2 times secant squared of x. Excuse me, I made a mistake here. I am just having a rough time of it tonight. That is not 1 minus secant squared. It is secant squared minus 1. One of those days. Not the most professional video I've done, but not the worst. So as we already said, distributing the secant of x to the negative 3/2 to the 1 is just going to give us secant of x to the negative 3/2. Secant of x to the negative 3/2 times secant of x squared is just a matter of adding the exponents, which is going to leave us with secant of x to the positive 1/2. And of course our secant x tangent x dx to the side over there. And at this point, we are ready to do our substitution. If we let u equal secant x, then we get du is equal to secant x times tangent x dx, which is exactly what we planned for at the beginning. Our integrand then can be rewritten as u to the 1/2 minus u to the negative 3/2 du. And we are ready to use the power rule. U to the 3/2 over 3/2 minus u to the negative 1/2 over negative 1/2 and of course our plus c. Fixing the fractions and resubstituting secant x for u. We have 2/3 times secant x to the 3/2 plus 2 times secant x to the negative 1/2 plus c. And again, this being calculus, it's acceptable to have fraction or negative fraction exponents. proper algebraic convention would suggest maybe you should rewrite at least the negative exponent with a positive exponent, but right now we're talking about a triviality. The idea is we got through the integration. So this was an example of splitting off a secant x and a tangent x. Let's take a look at another example. This time, it will be a situation where we have to split off a secant squared of x. This time, our integral is secant to the fourth of 3x times tangent cubed of 3x dx. Now, just to start out, that 3x that is inside both of the trig functions is probably going to just get annoying as we go through this problem. So it's not a bad idea to maybe just do a quick substitution at the beginning to get that out of the way. A quick substitution will just get that out of the way, get it out of our hair, and allow us to focus on the powers of secant and tangent. So that'll allow us to bring the 1/3 out in front. We'll just leave it there. And now we're going to have secant to the fourth of u times tangent cubed of u du. And that's just going to make our lives a bit easier. It just takes that 3x out of our hair. We, of course, will have to put it back in later, but for now, it gets it out of the way. So, in this case, we actually do have a couple of options. We do have an odd power of tangent, so I suppose what we could do is split off a secant and a tangent. That would drop the tangent cubed to a tangent squared, and we can use a Pythagorean identity. But we already used, in the previous example, splitting off a secant and a tangent. In this case, I'd rather take the other approach. We have an even power of secant, which means I can split off a secant squared and still have an even power of secant left behind. So that's the approach I'm going to take here. I have 4 factors of secant. So I'm going to keep 2 of them, and I'm going to split off the other 2 and leave them with the du. That will allow us to convert everything to tangents and eventually use the substitution with tangent as the inside function, and therefore that secant squared off to the side would be the derivative of my inside function. We'll have to be careful here because I already used u as a substitution variable, so we're going to have to use a different variable later. But the idea here is that we can take the even positive power of secant squared, and we can rewrite it as tangent squared of u plus 1. Times the tangent cubed we already have, and then our trusty little secant squared of u du off to the side. And from here, I hope it should be relatively obvious what to do. We can distribute the tangent cubed to make this into tangent to the 5th of u plus tangent cubed of u, and then times our secant squared of u du. And now we're ready to do our other substitution. Again, let's avoid using the variable u. We've already used it for something. So let's this time maybe pick out w. Let's let w equal tangent of u, so that dw is going to equal secant squared of u du. So we still have that 1/3 out front. Tangent to the 5th of u is now going to become w to the fifth. Tangent cubed of u is now going to become w to the third. And the secant squared u, du, is going to come out and become dw. So once again, we are set and ready to use the power rule here. Let's remember that that 1/3 is going to apply to the entire antiderivative. So this is going to be w to the sixth over 6 plus w to the fourth over 4 plus our c off to the side there. So we have 2 layers of substitution to back out through. The w has to come out and get reverted to tangent of u. So distributing the 1/3 will give us a denominator of 18, and in the numerator we're now going to have tangent to the sixth of u. For the second fraction, we're now going to have 12 in the denominator, and the numerator we will have tangent to the fourth of u, and then our plus c. One more layer of substitution to back out of. The u's now have to be replaced by 3x's. So tangent to the sixth of 3x over 18 plus tangent to the fourth of 3x over 12 plus c. None of these problems are small. Those days are long since past. Expect that problems are going to take many lines of work, such as we see here. Now, like with the sines and cosines, there were the common situations where we were able to split off what we needed to be the derivative of the inside function for the eventual substitution that was going to come along. But there was also an example at the end where we weren't able to do that because the powers just did not allow for it. Let's look at an example with that here. Let's throw in one extra little wrinkle and make this a definite integral. In this case, all we have is tangent to the fourth of x. I can't split off any factors of secant of x, which was necessary for both of the previous examples, whether it was a single factor of secant of x along with a factor of tangent, or whether it was 2 factors of secant x. But either way, we needed to have a factor of secant x to work with. We don't have that here. That being said, we do still at least have an even power of tangent of x, and that's a good sign, because that means we can use a Pythagorean, or the Pythagorean identity to do this. Now, I'm not going to bother with the definite integral part first. I'm going to focus just on getting the antiderivative, and then we'll deal with the fundamental theorem of calculus to evaluate this. So I'm going to make my life simpler by just focusing on the indefinite integral first. And what we can do here is write this as tangent squared x times a second tangent squared x dx. And one of those tangent squareds can be replaced using the Pythagorean identity secant squared x minus 1. Now you might ask, why don't I do that with both of them? Well, remember, in the previous 2 examples, the idea was that we had a mix of tangents and secants. If I convert all of the tangents to secants, then I'm not really fixing my problem because I'm just switching it out from a single trigonometric function to a different single trigonometric function. In keeping a couple of tangents and letting the others switch to secants, I now am going to get a mix of tangents and secants which is actually going to allow us to work with this pretty well. So let's start by distributing the tangent squared. This actually works out very, very well. If we look at the first term in there, we have exactly the kind of situation that we saw in the first example. We have two factors of secant sitting right there. So, giving myself a little more room here, I'm actually going to split this into two different integrals because the first part of this is ready to go. In this first one, I can simply do u equals tangent x with du equals secant squared of x dx. And that first integral is going to be very easy and clean to work with because it's simply going to become u squared du. Nice and clean. That second integral, however, is actually not unlike the integral we started with in that we, again, have an even power of tangent. Well, maybe let's try the same approach again. Maybe let's call this, again, secant squared x minus 1. And this actually works out very well. Once again, I'm going to separate this into two separate integrals. So we're going to have our integral of u squared du up front. Then we're going to have minus the integral of secant squared of x dx, which is a straightforward integral. The antiderivative of secant squared of x is simply tangent of x. So we can do that directly. Don't forget the distribution of the subtraction, namely this, so that we will end up with plus the integral of 1 dx. And now this should be pretty easy to do. U cubed over 3 minus tangent of x plus x. Now, we don't need to bother with the plus c here because, remember, this was originally a definite integral. So we don't actually need the constant of integration. You can write it. It will cancel itself out on its own. I'm going to save us a little bit of time and not write it. But we are going to have to go back to our original tangent here. So we have tangent cubed of x over 3 minus tangent to the first of x plus x. And this is our antiderivative. We can now apply the fundamental theorem of calculus to evaluate the definite integral. So the definite integral from 0 to pi over 4 of our original integrand, tangent to the fourth of x dx, is now going to be equal to the antiderivative, tangent cubed of x over 3, minus tangent of x plus x, evaluated at pi over 4, minus the antiderivative evaluated at 0. This isn't all that hard to work with, actually. Pi over 4 is a very friendly value to evaluate the tangent function at. Likewise, 0 is also very nice to evaluate the tangent function at. Tangent to pi over 4 is simply positive 1. And any power of positive 1 is 1. So in the first set of brackets, the numerator simply is 1. So we have 1/3 minus 1 plus pi over 4. And then tangent of 0 is 0. So all three terms in that second set of brackets are just 0. So what we end up with here is negative 2/3 plus pi over 4, which to me is an acceptable way to leave the answer. This is in its exact form. Because of the pi, the decimal equivalent of this is irrational. We'll have an infinite number of decimal places. I suppose we could find a common denominator and write it as a single fraction, but all of these are semantics. This is the exact form of the answer and is a perfectly acceptable value to write. That being said, if you were going to use your calculator to check your answer for this, you would probably want to evaluate that answer and find its decimal equivalent, and then evaluate the integral in the calculator and verify that the two decimal values it gave you were the same.